Hello and welcome. So let's talk about IPv4 header in this slide. So let's head over to the next slide, which is talking about the agenda, and agenda is very similar to the all previous sessions. Like we are going to talk about what is IPv4 from the perspective of troubleshooting, then from the perspective of network security, and then in the end we are going to do assignments. So let's go to the next slide, which is talking about the definition of IPv4. So the IPv4 is currently intact and dominant, but we have a new versions called IPv6. But IPv6 is starting to gain more attraction, and we are going to talk about IPv6 a lot in detail in a uh, future videos. So basically, if we talk about the OSI layers, we have application layer plus presentation and session. So these all comes under one layer. Let's make it like this. Then we have transport layer where we have to decide our data will be transmitted secure, in acknowledgement fashion or in a UDP, which is without acknowledgement. So we are going to use TCP or UDP along with some ports. Then we have which was a layer? The network layer. And the network layer, we know that logical IP addressing is works, which is IPv4. So this is where we have IPv4 resides. So that is why it is said that reside at OSI layer number 3, which is networking layer. It means we are going to find the best path using these logical IP addressing. So these things will come later. So after circuit switching, there is a need of packet switching. So I'm gonna take you back to the history. When we have these, telephone lines and they are connected with some wires. So basically we have this one telephone here, another telephone here, and these are kind of can say circuit switching connections. Whenever this circuit is on, okay, whenever this circuit is available and on, you are able to communicate, okay. But then the need came when somebody thought that we can if we can send the voice, why not we can send the data. So this is where the need of packet switching came in. Okay, so packet switching, how it works, we have, let's suppose we have one source and then we have some destination. If you familiar, the circuit switching works in single pattern, okay, one source, one destination, and one path. But in case of packet switching, we are not going to follow a single path. Let's suppose we have multiple routers in between. Okay, so this is a source, this is a destination. So the my data will travel from this source. Either it could take this path to reach the destination, or it could take this path to reach the destination. So it means the packet switching has multiple redundancy involved in between. So that is, a very handy concept. That is the use where we use IPv4. This is connectionless because unlike the TCP, because we already talked about TCP, its use was sequencing and acknowledgement to make sure the data is there. But IPv4 unfortunately is connectionless. But router has its own mechanism to find whether the data has reached or not. But this IPv4 is connectionless. So it will send the data and it will not be acknowledged. And when I will hit IPv4 header, you will see there is no any field regarding sequence and acknowledgement, something like that. Then encapsulation as a header, because remember from the OSL layer, whenever we are going to move from top to bottom, it is going to encapsulate the data. So it is going to encapsulate its header, and header is having the information about the source and destination IP. And this is structured data to be transmitted across the routed network, and more coming into it in the next slides. Okay, so let's head over there, which is talking about the IPv4 header. So this is 32-bit long IPv4 header, and you can see there are so many things. So first, the things that we already familiar from our previous headers that we have talked about, like TCP. So source IP address. We know this is the source IP address. Let's suppose this is 192.168.1.1. And this is the destination IP address that we are heading toward. Like job skill share IP address. Let's say the job skill share IP address is like 90 99.1.64.70. So this is the source field, this is the destination. Then we have a version field. Version could be IPv4 or IPv6. Then this is header length, okay, the length of this whole header. Then these are the type of services. Sometime, we have to give the priority to the service. For example, if it is related to voice, it has different priority, could be a higher priority like 100. If it is like data, it has a low priority like could be 80. So whenever the packet will come, this voice will be given more priority. So this is has to do with the quality of services. Then this is the total length of the data. Then this is the identification field, and identification plus flags, they are interrelated with each other, because when the communication happens from source to destination, the chances are the chances are, if the packet size is larger, and in between device that is going to receive that packet maybe does not have capability to process that higher data. For example, the data size, let's say 1500 byte of size, and let's suppose this router is capable of handling only 500 bytes of data. So what it is going to do, it is going to divide that large packet into multiplied by 3 packets. So 500 header, sorry, packet, 500 packet, and 500. Usually this is called frame, because we have header involved from the Ethernet. So that is why you usually call it headers, but you can call it the packet size. So the packet size is 500 byte, 500 byte, and 500 byte to accommodate 1500. So this is where we need to provide the identification. So these all packets, since they are related to one single communication, maybe the identification of this packet is like A123, A123, A123. So this is how the destination, when it is going to receive, it has a clear understanding this is coming from the same um, communication. And this is not only the case, we have another case when we have one source, we have one destination, but in between we have multiple paths to reach. Okay, so it can follow multiple paths. So the chances are, what in case if this single packet with 1500 byte is divided into three packets of 500 size, and one packet is took this destination or follow this path, another packet took this path. So this is where the identification will be helpful at the destination end. And by the way, whatever this scenario is happening here is called fragmentation, and that is why we have to do with the fragmentation offset. So this field is going to identify whether the fragmentation is happening or not. Then we have protocol field. Protocol field, we know that at OSI layer, if IPv4 working at network layer, it is going to receive this information from transport layer. And transport layer, we know that what protocol works, TCP and UDP. And if the protocol field is set to like uh, 17, it means it is correlated with the UDP. So the information that is receiving from the UDP, and in case if it is 6, it is representing TCP. So this protocol field could be 6 or 17, depending on what kind of protocol you are receiving from the transport. We have time to live. This is the basically the mathematical formula using 2 power. Okay, but it starts from the higher number. It could be 256, 128, 64, 32, something like that. Okay, so what is time to live? Time to live is, for example, we have source, we have destination. In between, we have multiple hops or paths. So as the data is transmitted, the TTL will be set accordingly, like 256 is set. This field has been set as 256. As the data or the packet will moves to next hop, to next hop, to next hop, this value will be decremented with -1. So from source it hit to the first router, the packet TTL value is 255. Then it reached here, the value is 254, 253, 252, and it hit the destination correctly. But what in case? But what in case if these all routers are connected together and there is some kind of corruption happens? The TTL is set to 255 or 256 initially. Then it leaves this router. The value is decremented to 254, then 253, and then unfortunately it didn't receive by the destination, but it loop around. Now you can imagine the TTL values will be decremented all the way to 255, to all the way to 50, to 40, to 30, to 20, to 1, and then as soon as it will hit 0, maybe it hit it 0 at this router. This router has a potential and intelligent enough to know that when the TTL value will become 0, I am going to drop this packet. So this is the mechanism to avoid loop in WAN environment. Okay, but in a LAN the story is different, because LAN does not um, in local area network LAN, where we are using switches does not understand the concept of IPv4. So that is why if we have loop in the switches, they usually stop these kind of uh, looping behavior using spanning tree protocol, STP. But that is different story and we are going to cover in our future videos. Then we have header checksum. Also we want to make sure there's a data integrity, so nothing has been changed during the communication or on a path. During the path there is no any kind of change. Then we have some options and the payload. This is going to be your data. So from the perspective of Wireshark, if I can show you, so if I will take you to the Wireshark, okay. So let's, as you can see, we have this. So I'm gonna use for that. Okay, no problem. So let's click local area connection, and you can see something is going on behind the scene. So stop the capture. Now you can see in a fraction of time how many packets we got, 34 packets. How many packets we dropped, 0%. Okay, displayed 34. So it means there is no any kind of lost packet. So let's head over to the TCP because it is going to unfold these all layers. So we are specifically talking about the network layer, which is concerned about Internet Protocol version 6. Okay. So in case if I get some version 4, let me see because this will be more helpful for you. Let's pick this one, Internet Protocol version 4. So as I said, the version field. So this is the representation of version 4. And this could be version 6 as well. Then header length is 20 byte because if you multiply version 4 with 5, 5 multiplied by 4, which is 20. Okay, so this is going to be the header length. Then in a slide, I talked about the type of services. Okay, if I'll take you to this slide, as you can see, the type of service. So these differentiated service field is basically the quality of service, which is set to 00 by default. But in Cisco routers, if you have set some kind of quality of services field, like for voice over IP, you are going to give more priority, then you will see different fields over here. Okay, here over. I'm not going to go a lot in detail what is these ECN checkpoints because we are at very basic level. We are just scratching the surface of these fields. So it has to do with quality of service. Then we have this total length, the size of this packet, and then this is the identification field I was talking about earlier. So as you can see, it has given identification 40682. And it is saying the don't fragment or fragment offset is 0. If you can correlate from here, fragment offset over here. So this is 0 means it is not going to fragment the data, or it is not going to basically divide that large packet into small packets. So fragment offset, don't fragment is set. And fragment offset has to do with, in case if the fragment is there, there is also going to be identification for the fragment offset. Then we have time to live, which is set to 128, which means the maximum hops it went uh, could be till 1, 128 all the way to 1. If it hits 0, it means my router is going to discard that packet. Then we have protocol, and as I told you over here, this is the protocol field. It could be 17 or 6, but in case this is representing 6, it means this is TCP because it received the packet from the TCP. As you can see, the protocol is TCP. So this is the identification of the protocol. Then we have a header checksum, and you can see validation is disabled, and why I'm going to discuss in the next slide. So but the header checksum, I have already told you what is the uh, basic mean of using this header checksum. Then we have source address and destination address. So this is all talking about the IPv4 header. So let's head over back to my slide. So we are done with the Wireshark. So from the perspective of troubleshoot, the most common issues that we face is issues or maximum transmission unit mismatch. I have already talked about what is MTU. Whenever you are going to send packet from source to destination, the packet size, let's suppose this is 1528 byte. So this is packet is size is set from source. But in between, if maybe there is a switch or the router does not capable of handling this large size of packet, it is going to divide into small chunks. Okay, that is called fragmentation. So on many occasions, many computers have, or sorry, devices have mismatch issues. So the maximum transmission unit MTU is a maximum frame size that can be sent between two hosts without fragmentation. The MX uses an MTU size of 1500 or 1518 bytes. So this is the large packet or 9600 bits, if you will, on the LAN WAN interface. So when a packet is sent from a local host to a host in a remote network, the frame may be traverse multiple router hops. Okay, so if the MTU size is set to too high and exceeds the limit of the underlying network infrastructure, fragmentation may occur. So fragmentation can impact network performance and increase the likelihood of the packet loss. So this could be the issue. On opposed to large size packet, we could have small size packet that's called runs. So runs are undersized packets smaller than what a network protocol calls for, such as 64 bytes in Ethernet. Okay. The large packet is called giant and the small packet is called runt. So these are technical terms you need to be aware of. So if I will give you a very good example from the command prompt, if I'll try to ping google.com with having these options set, and I will show you. So let me just copy this command. So basically this is the ping command. So let me copy and let me take you to the command prompt. Command prompt. And if I try to ping, first of all, I will just simply ping whether do I have the reachability to google.com. Yes, it has. Now I am going to ping using setting these fragmentation of options. So as you can see, I have set the fragmentation of 1472 byte. If I'll try to, now you can see the fragmentation, it is fragmented, but DF is not set. So it means still my fragmentation is not working accordingly unless until you are going to tune this size. So you need to, as it is mentioned, you need to decrease until you get a reply. Okay, so let's decrement the size of this fragmentation to 1 and let's see if we are getting response. No. Let's make it to 70. No. Now let's make it to 60, 1460 byte, and you can see now this time I am going to get the reply. So this is the MTU size that my source machine to reach to the destination has to be to agreement on. So we have to agree on this packet size in order to communicate. If we not, you can see we are going to lose the packet. Okay, I hope you get the idea. So from the perspective of cybersecurity and network security, and as you can see, as I said, the IPv4 has a header which can be compromised. We have already talked about data integrity. Means if the packet is um, uh, sent from the source to the destination, and the chances are in between somebody could manipulate this IPv4 header. So instead of the source IP, the the hacker, he could have its own IP source address, which is not legitimate. So this is the IP address of hacker. So once the destination is going to reply back, it is not going to go to the source, but is going to go to the hacker machine. Got it? Okay, there is another issue called header checksum issues. If you do a Wireshark packet analysis, you will see some kind of these issues. Header checksum incorrect, should be this, may be caused by IP checksum offload. Okay, so these are the problem happens. By the way, this is not the issue. The issue is, you know, before the data, for this is your network, not, this is your NIC card, network interface card, where this RJ45 connector is plugged in. Maybe the data is coming from your ISP. Okay, so the data is coming and data is going. Network interface card and our Wireshark is capturing these all packets from this RJ45. Sorry, network interface card. So when the data, as soon as it hits the packet, our Wireshark is capturing those packets. That is making these checksum offload issues. But this actually is not the issue, because network interface card is going to process that data over here, and then it is going to send the information to the source machine. Whereas the Wireshark is quick enough to capture that packet even before processing that packet. So that is why these kind of things happens in a Wireshark. To mitigate this issue, what you can do, you can go into the Wireshark, you can go into the edit section and go into the preferences under protocols, and we are talking about the IPv4. You can see under IPv4 we have validated the IPv4 checksum if possible is disabled. If we enable this one, let's suppose enable this one, click OK, and you can see I have started to get these errors. So in order to mitigate, edit preferences under protocols, then we have IPv4, and then we need to disable this checksum and click OK, and you can see the error has gone. Then we have another issue or attack that is called TTL expiry attacks. So cyber criminals can adversely affect the CPU load using TTL expiry attack. This is just like denial of service kind of attacks. Okay, so an attacker sends out a massive amount of packets to the destination host with a TTL value less than or equal to t minus 1, where it represent the time to reach the destination. So when packet reach the last router before the destination, TTL value is set to 1. So basically what happens? Let's suppose we have multiple routers in between, and my packet is going to loop around. And usually when TTL becomes 0, my router is going to drop that packet. But what hacker will do? He will use these kind of mathematic, uh, you know, um, these kind of mathematical values to inject into our these TTLs. So whenever it is going to be 0, it is converted into 1. So it is never going to go beyond 1. So it is not never going to be 0. So that is why If the TTL is 1, it is going to loop around. And similarly, the hacker is going to send thousands and thousands of packets, will choke up your network completely. So the solution, the mitigation. Security controls should filter packets with the low TTL values to protect them. So if the TTL, let's make it in our, for example, firewall or intrusion detection or IPS protection systems. If you say kindly devices, if the TTL value go beyond 10, discard that packet. So instead of, going to 0 and then discarding, you can low TTL values as much as possible. Okay, so this is the mitigation. So common interview question and answers. So how many bits are used in IPv4 address? What is the importance of identification field? Which device can resemble the packet? What is fragmentation and what is the importance of TTL field? Okay, so with that, our IPv4 video comes to end, and I hope you enjoyed this video, and I'm gonna see you